Topic 10, regressions with time series data, non-stationary variable. Okay, let's start with looking through a number of time series generated by an AR1 process. For example, like this one. The process is yt is equal to 0.7 yt minus 1 plus vt, where vt is the standard normally distributed. Look at the graph here. First, we can see that it is stationary. This process is stationary. Being stationary means the mean of yt in these cases is actually equal to 0. It does not depend on time. Also, variance, we can show that variance of yt is constant across time. Does not depends on time. In addition, the covariance yt and let's say yt minus s will only depends on the how far away from t to t minus x, the time length from t to t minus s, or the s. So it depends on s. And s increases, this covariance decreases. Or correspondingly, the correlation, which is covariance of yt minus 1 divided by the standard deviation, or variance of yt square root of variance of yt minus 1, decrease to 0 quickly. And this graph shows the sample autocorrelations. We can see that, okay, let's look at the horizontal axis is a lag. For example, here 0 lag, which by definition the correlation will be equal to 1. Okay, then 1 lag, 2 lag, so on and so forth. We can see that quickly decay, drop to 0. So this process is stationary. Another feature we can observe here is that it has a mean reversion. If for some reason it goes far away, the mean here is 0, go far away from 0, then it will return back, or go far away from 0, return back. So there's kind of mean reversion. So this process is stationary. Okay, let's look at yt is equal to 1 plus 0.7 yt minus 1 plus vt. So now the difference is we have extra terms 1 here. Still stationary, still the sample autocorrelation decays quickly. Also the variance roughly the same. Variance constant across times, and the difference is the difference from the previous picture is that now the mean is roughly 3.33. It's no longer 0 because we have extra constant here. Okay, let's look at this process. Yt is equal to 1 plus 0.01 t plus vt is standard normally distributed. So now we have these terms here, 0.01 times t. So we are having this deterministic time trend. So we see that indeed the graph here is increasing over times. So now the sample autocorrelations, it does not decay like quickly, right? So it's kind of very, very persistent here. In such cases, this process is not stationary. Clearly, mean will not be constant across time because we see that it's increasing deterministically across time. The further the farther away, the higher means yt is going to have. So clearly, this is not stationary. But if we get rid of the time trends, means that we look at yt, take away the time trends 0.01 times t. We can regress yt against time and predict the residuals in -1, let's say. Then we get a stationary process. So essentially, we get a VT, and VT by definition is RID across times. So we call this process trend stationary process. Right. In our regression, if our variable is trend stationary, then we can just include a time trend to account for this, and then that'll be fine. Okay, let's look at this process. So this is also trend stationary. It has a deterministic trend. This is yt is equal to 1 plus 0.01 t plus 0.7 yt minus 1 plus vt. So there's still a deterministic time trend here. And we can see that despite this component is stationary, okay, we can still see that the sample autocorrelation is such very, very persistent. And there's increasing time trends. So this process is not stationary, but it is trend stationary. If we remove the time trends, we can obtain a stationary process. Okay, let's look at this. This is called random walk. Yt is equal to yt minus 1 plus vt. Previously, we have this yt is equal to rho yt minus 1 plus vt, and where rho is equal to 0.7. In contrast, now rho is equal to 1 here. Rho equal to 1. Okay. So this is one realization of this process. We can see that this process it kind of wanders slowly upward or downward with no real pattern. So it goes up, then goes down slowly, goes down slowly, then maybe goes up, goes down, with really no time patterns. Also, if we check the sample autocorrelations, we can find that it is quite persistent. It does not decay quickly. Okay, so this process is not stationary. It's actually non-stationary. Or we can see that it contains a stochastic trend. Previously we have deterministic trend, right? So now we have stochastic trend. Okay, what do we mean by these stochastic trends? So this is our random walk process where Vt is RID, standard normally distributed. Okay, so let's start with t equal to 1. Yt is y0 plus v1. Then y2, second period, will be y1 from this equation. Let's do this computation recursively. y1 plus v2. y1 in turn is equal to y0 plus v2. So this is y1. So we got y0 plus v1 and v2. And y3 will be equal to y2 plus v3. And y2 we have the formula here, so we should y0 plus v1 plus v2 plus v3. So on and so forth. We can write yt as y0 plus the sum of v from time 1 to t, v1, v2, v3, vt. Okay, and this sum we call this stochastic trend. So now we can see that this random walk consists a terms we call this stochastic trend. Okay, let's check the expected value. Taking expectation, okay, y0 is here, so we get, and bear in mind that Vs, they are independent. They are actually standard normally distributed. So we can take expectation y0 plus sum of from 1 to t Vs. So we can move inside. This expectation is a linear operator, so it's y0 is kind of constant. Okay, so the initial value plus sum of s equal to 1 t EVS is equal to 0 because it's the mean of the standard normal distribution. So we get y0. The variance, this is constant terms, it drops, so variance of y0 plus sum of Vs. So this is constant, so this is equal to variance of, we can drop, because y0 is the initial value, we treat it as constant, so we drop from the equation, sum of Vs. So now, because of Vs, V1, V2, Vt, they are independent, so we can exchange, we can pull the summation outside the variance. And this, okay, here is sigma V squared, but in our simulation here, sigma V squared is equal to 1, but let's use suppose it's 1, okay, then we get sum of 1 is from 1 to t, so which is t. So there are t ones, add them up, we get t. So now we can see that this variance depends on time, clearly. So let's say is that this random walk is not stationary, and we also call that this random walk contains a stochastic trend. Okay. Alright, sometimes we can have random walk with drift. So yt is yt minus 1 plus vt, and delta is a constant term. This delta is called drift, and a realization of this process looks like this. So it's kind of wandering around, and clearly the sample autocorrelation is very persistent. So this process is not stationary. Okay, let's look at the last one. This process is equal to yt is 0.1 plus 0.01 t plus yt minus 1 plus vt. So it contains a random walk component also, which is a stochastic trend and a deterministic trend. Two components. So yt now contains both deterministic and the stochastic trend. So this is one realization, and we can see that the sample autocorrelation is highly persistent. Okay, very persistent. Again, this process is not stationary. Right, so we see that time series, a process can be stationary. Then we now know how to analyze them. For example, using ARDL estimate in autoregressive distributed like models, as we did previously. Time series can also be trend stationary. It contains a deterministic trend. So to handle this trend stationary variable, it is in a sense easy. So we just need to include the time trends in the regression. okay, to account for this time trend. Or we can detrend, we can perform analysis on the detrended variables. Time series can also be non-stationary, which is, we say that it contains a stochastic trend. Okay, now you need to ask, why does this matter? And how can we analyze it? Okay, let's check why does it matter. To see the undesirable consequence of non-stationarity, well, this was artificially generated two time series. This is called X and Y. And we can regress Y over X, one against the other. And be aware that we artificially generate these two time series. We generate them independently, separate. So we should not expect to find a significant impact of X on Y. If we regress Y on X, then we shouldn't find a significant impact of X on Y, because we just artificially generated these two time series independently. Okay, and this is the case for cross-sectional data. If, say, for the cross-sectional data, I randomly draw 500Y, randomly draw 500X, regress Y against X, I will not find a statistically significant impact of X on Y. For example, like this. Let's draw 500Y from the standard normal distribution, 500X from standard normal distribution, and regress Y against X. So this is output of R. Okay, we can see that indeed, the coefficients of X, the intercept, they are all not statistically significant, and the R squares or adjusted R square is very small, almost zero. Which makes sense that they should be. This is Y, this is X. They should be something like very randomly scattered. There's no association between Y and X at all. Okay, and our F-test statistic is only 2.484 with a p-value 0.1157. Also suggests that overall it's not significant our regression. So this makes sense in cross-sectional data. What about time series data? Okay, let's generate two time series data with stochastic chain. So first series YT is equal to YT minus 1 plus V1T. V1T is RID, standard normally distributed. And initial value, let's start with 0. Similarly for X. Okay, and the red curves here is YT, blue one is XT, and ideally, or since we generate this data, we know that there shouldn't be any impact from X to Y, right? But now let's regress Y against X. So this is the regression output in R, and the intercept, the coefficient of X, is negative 0.53774 with a t value standard error of 0.018, t value of negative 29.73. So we find that there's a statistically significant impact of X on Y now using this time series data, despite we know that we artificially generate them independently. So now we end up in having this kind of undesirable relationship between X and Y. And also, if we check the R square, adjusted R square, they are very high, 0.63, and F stat is very high with p-value less than 5%. So everything points towards that our regression says that okay, X affect Y significantly, but we generate data, we know this, there shouldn't be any impact of X on Y. So this is troublesome. So we call this relationship is spurious, or the regression is spurious regressions. So we generate data and know that there's no relationship between x and y. Yet we end up in discovering a statistically significant impact of x on y. And this is all the fault of this stochastic trends. Okay. And if we, after the regression, if we predict residuals, we're going to find that the residuals themselves are non-stationary. This is the residuals plot. Is quite persistent up to almost like 25 likes, and it also kind of wandering around with really no patterns. Okay, so this is the undesired consequence of stochastic trends. We end up in having these spurious regressions. Despite x has no relationship with y, we end up in finding a y. Okay, so in our regression, in our estimation, we need to avoid including such kind of non-stationary variables. So we need to test for the stationarity of the time series. And there are many tests for this purpose. For example, Phillips-Perron test, KPSS test. For our purpose, we are focused on the Dickey-Fuller test for unit root. Okay, now there's a new terms, new jargon coming up. Unit root. What does it mean by unit root? Okay, let's look at the AR1 process. Yt is alpha plus rho times yt minus 1 plus mu t. If absolute value rho is less than 1, then this process is stationary. Okay, it converges in a sense. Okay, or in contrast, if rho is equal to 1, we end up in having a random walk. Okay, and it's non-stationary. We have seen this previously. In these cases, we say that yt has a unit root. Okay, to be more precise, let's look at ARP process. Yt is alpha plus theta 1 times yt minus 1 plus theta 2 times yt minus 2 plus until theta p times yt minus 3 plus vt. And we're going to introduce a lag operator. For example, LYT. That means we're going to lag yt by 1 period. So we get yt minus 1. If we lag yt by 2 periods, L2yt, then we get yt minus 2. More generally, LPyt, we get yt minus p, so on and so forth. Okay. So we can rewrite this ARP process as yt is equal to alpha plus theta 1 times Lyt, so on and so forth. Okay, so now we have yt common terms here, common terms here. So we can move all these terms to the other side. We get yt minus theta 1 Lyt minus theta 2 L2yt minus theta p Lpyt. So now we have yt terms on the left hand side. This yt common term we can pull it out. So we get yt times 1 minus theta 1 L minus theta 2 L square minus theta p Lp square. And you know that this is a polynomial function on L. So we can write, more generally, we can write this as theta j. Phi j is equal to 1 minus theta 1j minus theta 2j square minus theta p jp to the power. So it's this. So the roots of this polynomial are the values of j such that the polynomial polynomials become zero, vanish. So now if one of these roots is equal to 1, then yt is said to have a union root. That's where the union root, this jargon, come from. Or equivalently, it has a stochastic trend and it is non-stationary. So back to AR1 process. So now this polynomial is just order 1, okay. Highest power is p, which is equal to 1. So the root of it is easy for us to find because it's a linear function. Theta 1 j is equal to 0. That implies that j is equal to 1 divided by 1 over theta 1. So if j is equal to 1, that implies that theta 1 is equal to 1. And remember, we said that previously, we said that in AR1, yt is theta 1 yt minus 1 plus vt. So is random walk if theta 1 is equal to 1. And random walk is non-stationary. So in these cases, yt is non-stationary. Okay, that's where the union root comes from. Right, so we want to test whether a time series is stationary or not. Here, as the usual process of hypothesis testings, we need to have the null hypothesis and alternative hypothesis. We have one null hypothesis for the Dickey-Fuller test. The null hypothesis is non-stationary random walk. So this yt will be equal to yt minus 1 plus vt, where vt presumably should not be correlated, autocorrelated. In contrast, the alternative, there could be 3 possible alternatives. That means we have 3 possible tests. First, this process has intercept in the no time trend, or with intercept and trend, with no intercept and no trend. Okay, let's go through them. So Dickey-Fuller test with intercept and no trend. So this is our null hypothesis. It's a random walk. This is our alternative. There's an intercept here. There's no time trend. Okay, so rho here under the alternative, rho is less than 1. So under the null random walk stationary, that's the same as saying that rho is equal to 1. So we are really testing the value of rho. And now you might be thinking about, then that's easy. We can run a regression and do a t-test, right? That you might be thinking about this. We have done t-test before, right? But let's be more careful than this, okay? Let's first manipulate the equation so that it becomes more convenient for us. So let's start with the alternative equation under the alternative. So yt is equal to alpha plus rho yt minus 1 plus vt. Take away yt minus 1 from both sides. So we get this equation. And this one becomes first difference of yt, okay, change of yt from previous period, plus alpha 1 equals alpha 1 plus rho minus 1 times yt minus 1. So here now let's call this gamma. So we arrive at this equation. dyt is equal to alpha plus gamma times yt minus 1 plus vt. So now our hypothesis become this. Now hypothesis rho equals 1 is equivalent to null hypothesis of gamma equal to 0. Right? Rho equal 1 is the same as saying that gamma equal to rho equal 1 is say, okay, this is gamma equal to 0. So gamma equal to 0. And typically we are going to test against one-sided one inequality, okay? So alternative is rho less than 1. That means gamma less than 0. Okay, so it's one-sided test. The test, so we regress this. Dyt is equal to alpha plus gamma yt minus 1 plus vt. We regress this equation and take the gamma, get a gamma estimate here, get a standard errors estimate, standard deviation. We form, you should see that now this is very much like a t. However, we're going to call this tau. So this tau no longer has a t distribution under the null. Remember, the null hypothesis is that our process yt is a random walk, it's non-stationary. So because yt is non-stationary and its variance increase, it's actually, we can show that it's actually t times sigma b squared increase over time. Okay, so now we get this tau no longer has a t distribution. That's why we are renaming this gamma hat over standard errors gamma hat as tau rather than called t. So now we must compare tau with specially generated critical values, and statisticians have tabulated critical values for these cases, and usually any packages that we use, they will generate report this critical value or more convenient associate p-values. Okay, so if now the p-value is less, let's choose alpha to 5%. If now the p-value is less than 5%, then we will reject the null of random walk or non-stationarity. Okay, we can also do the test with intercept and no trend. So like this, and we are estimating. Okay, we are assuming that the estimating equation have intercept and no trend. Okay, and here when we estimate this equation, we assume Vt has no serial correlations. If not, okay, remember we are in the time series framework, so autocorrelation, serial correlation is not uncommon. So we can augment it with a lagged dependence of y to absorb these autocorrelations. So we get this, we add this lag of difference to y from for p-1 period. And this is what we call augmented Dickey-Fuller test. And this corresponds to yt is an ARP process. Okay, the second variety and third variety are here. Augmented Dickey-Fuller test with intercept and trend. So now we have a time trend, deterministic time trend here. Everything else the same. And or we can no time trend and no intercept. So this no time trend, no intercept. In practice, we can first visually examine the time series plot to see which situation shows best. We can also conduct all three tests to check the robustness of our stationarity tests. Okay. Typically, in practice, a time series is non-stationary and labeled. So yt, say yt, this process is non-stationary and is labeled. However, it will be, if we differentiate delta yt, remember this is yt minus 1. If we differentiate, it becomes stationary. In these cases, we call yt is integrated. We call yt is integrated of order 1, denoted as I1. Okay. If yt is already stationary in labels, then we say that yt is integrated of order 0 or I0. So we have a process could be I0 stationary, I1 non-stationary in label but stationary in and difference and false difference. Sometimes we can have a process of I2, which means that it's non-stationary in label, also non-stationary and false difference, but it's stationary and difference of differences. Okay, so second difference, d2yt, delta 2yt, that will be stationary. That means that's equal to delta yt minus delta yt minus 1. Okay, difference the yt by twice. Sometimes we can I2. Really, we don't have any order of integration higher than 2. Okay, as a general rule, to avoid the problem of spurious regression, non-stationary time series variables should not be used in a regression model, at least directly. Typically, if yt and xt they are I1, okay, non-stationary and label, but stationary and false difference, then we expect the difference. For example, let's say et is yt, the difference yt minus beta 1 minus beta 2 xt to be I1 as well. And this is the case in our previous spurious regression examples. Typically, that's the case. However, there's one exception. If this difference et turns out to be I0, it's stationary. Now we're going to say that yt and xt are co-integrated. In such cases, we can regress y against x. Actually, the estimator would be called super consistent. It converges. We can show that it converges to the true value faster than otherwise. Okay. So we have the possibility that two I1 time series can be co-integrated. That means the linear combination of difference becomes I0. So co-integration implies that yt and xt share similar stochastic chain, and as such, they never diverge too far away from each other. So now, if we have two I1 time series, or maybe many more than two, that's fine as well. And economic theory suggests that yt is a linear function of x, depends on x. Okay, conceptually at least. Then what we can do is we can regress y against x to estimate this relationship. Or if we have more than one x, x1, x2, x1t, x2t, x3t, xkt, we can do a regression, regress y against x1t, x2t, x3t, so on and so forth. And then now we need to make sure that indeed they are co-integrated. So let's predict residuals, and the test is test the stationarity of the residuals. So here a point of that we need to be aware that in testing the stationarity of residuals, we are predicting the residuals, they are predicted values. So the critical value need to account for the fact that the test is based on the estimated value of residuals. Okay. So again, if we use proper statistic package, this will be accounted for automatically by the package. So if the residuals are stationary, then we can conclude that yt and xt, or yt and x1t, x2t, xkt are co-integrated. And this estimated, say, yt is b1 plus b2 xt, then this equation captures a long-run relationship between y and x. Okay. So now we have a long-run relationship. Remember, bear in mind that we are in a time series framework. So here dynamics is important. Okay. Coordinate equation. What does it mean? It's the relationship between two I1 variables, two or more I1 variables, such that their residuals are I0. So we call the relationship between two I1 variables. Often we call this as a long-run relationship. Okay. In contrast, if it is a relationship between I0 variables, we often call this short-run relationship. Okay. And recall that we have ARD autoregressive distributed lag model with lag P and Q. And now we're going to show that we can actually, in last week we said that we need the variables to be stationary. Actually, we can allow for I1 variables. And furthermore, we can build this long-run relationship, this coordinate equation between I1 variables into this ARDL. And then we resulting in error correction models. Okay. So let's start with ARDL 1-1. So yt is equal to delta and theta, they are parameters. Okay. Delta plus theta 1 yt minus 1 plus delta 0 xt plus delta 1 xt minus 1 plus vt. If y and x are co-integrated, then there's a long-run relationship between them. Okay. So let's impose the steady state condition to derive the long-run relationship. In the long run, y and x are at the steady state. So now we have y is equal to delta plus theta 1y plus delta 0x plus delta 1x, and let's ignore error terms. Suppose in the long run we don't have errors. Okay. So now we move this term to the other side, combine these two terms. So 1 minus theta 1 y is equal to delta plus delta 0 plus delta 1 x. Divided both sides by 1 minus theta 1. We get delta 1 minus theta 1 plus delta 0 plus delta 1 minus theta 1 plus x. So we actually get this equation, and these terms we call beta 1. This terms is beta 2. So that's the long-run relationship between y and x. Okay, so now we start with ARDL 1-1. We derive the long-run relationship between y and x by imposing the steady state conditions. Let's manipulate this ARDL 1-1 to embed this long-run relationship, this co-integrating relationship into this ARDL 1-1 model. So that's our starting point. Take away yt minus 1 on the both sides. Okay, so we get this one and this one. Okay, and I'm gonna add delta t, take away delta 0 times xt minus 1, then add the same terms, so it doesn't change. Combine these terms with these terms, we get these terms. Okay, delta 0 times xt minus 1, and these terms combined with these terms, we get delta 0 plus delta 1 times xt minus 1. Okay, and let's call this yt minus 1. Let's call it denoted it as delta yt minus 1, and similarly for delta t delta xt. So on the left hand side we get delta t minus 1. On the right hand side, let's pull. Okay, let's work on these terms. Okay, these terms, and pull theta minus 1 out of the whole terms. Okay, so yt minus 1, we pull it out, we get this. And we have terms delta. So delta pulled theta 1 minus 1, we get a delta, we get this theta 1 minus 1 times theta 1 minus 1, and this get pulled out here. So we get a delta divided by theta 1 minus 1, and this is equal to delta, negative delta divided by 1 minus theta 1. So we get this term. That's where this term comes from. For xt minus 1, so we got delta 0 plus delta 1 divided by theta 1 minus 1, and that's the same as minus, pull the minus signs in the front, we get divided by 1 minus theta 1, we get this. And you might be wondering why we are doing so, because now since terms inside this bracket looks exactly the same as our long-run relationship we just derived a moment ago. So we know that this is called beta 1, this is called beta 2, right? So now we have this equation, and let's call this alpha. This called alpha to be 1 minus theta 1. So we have this equation. This ARDL, we manipulate the algebra such that we arrive at a forms that give us the interpretation of error corrections that embed the long-run relationship into our equations. And we now want to observe that why this is called error correction. Okay. So this is a long-run relationship. So we know that long-run relationship y minus, in the long run, beta 1 minus beta 2x, or y is equal to beta 1 plus beta 2x. That means 1 minus beta 1 minus beta 2 times x is equal to 0. In the long run, that's a long-run relationship. However, we can be above the long run, below the long run. Suppose this difference for t minus 1, for the period t minus 1 is positive. So now t minus 1 is above the long run levels. Then in period t, this is positive, so alpha is positive, so negative alpha is negative. That means delta yt now is negative. Delta yt is negative. So now that means yt minus 1 goes down, should be below, should be smaller than yt minus 1. And remember, yt minus 1 is, so this, suppose this is our long run level. And we know that yt minus 1 is at this level, and which is above the long run relationship. However, delta yt is negative, which means that yt is less than yt minus 1. So yt should be smaller, should be below yt minus 1. So we're getting kind of correction, because yt is too high above the long run relations. So there's a correction, there's a downward correction, so that yt getting moves towards the long run relationship. If in contrast, if this is negative, then situation is this: yt minus 1 is here below the long run average. Then this is negative times a negative terms, we get a positive. So yt will be increase, moving towards the long run relationship, long run level. So that's why it's called error corrections. Okay, so far we see that we can account for both short-run and long-run dynamics in ARDL models. And we can also accommodate both I1 and I0 variables in the ARDL. The question is, how can we estimate these models? So this is what we want to estimate. We can regress delta t, delta yt against the yt minus 1, xt minus 1, or delta xt. So estimate this equation. And let's call this intercept beta 1 star, alpha star, beta 2 star, d0. Then we compute the corresponding alpha, which is negative alpha star, beta, which beta here, which we see that for xt, let's look at xt minus 1, the coefficient xt minus 1. So alpha beta 2 is beta 2 star. So beta 2 will be beta 2 star divided alpha, or minus beta 2 star divided by alpha star. It is similar for beta 1. Then we can compute the standard errors through the delta methods. That's how we can do the estimations. Alright, what happens when there's no co-integrations between I1 variables? If so, one way to accommodate this is to convert I1 variables into I0 by differencing, first differencing, then use the differenced variables in the regression. That's the easiest way to accommodate the I1 variables. Okay, that's all we want to cover about the time series analysis. This is an introductory topic. Okay, so if you are interested to understand more about the time series econometrics, you can do a subject that's dedicated to time series analysis. All right, let's have a quick summary. So we want to do regressions with non-stationary variables. Let's check whether these variables are trend stationary, which means that if we take a trend, regress these variables against time, predict the residuals. If the residuals are stationary, then these variables is trend stationary. Then we can estimate in ARDL models in levels, okay, including a trend terms to account for these trends, and that will be enough. If in contrast it has a stochastic trend is I1, then let's check whether these variables are co-integrated. We regress one against the other. Well, do we end up in having I0? Do we end up having stationary residuals? If yes, then they are co-integrated. Otherwise, they are not co-integrated. If they are co-integrated, we can either estimate a long-run relationship with ordinary least square estimators, or we can estimate short-run error correction models. Okay. If we don't have these I1 variables are not co-integrated, then we can estimate ARDL models in force differences. Okay, that's all about what we want to cover for this subject.